Okay, in this lesson we're going to talk about solving linear systems by graphing. First of all, here's an example of two equations that form what's called a system of linear equations. You have 2x plus 3y equals 8, 5x minus 2y equals 4. Each of those linear equations is given in standard form. A solution to this system of linear equations is going to be an ordered pair xy that would satisfy each equation in the system. In other words, if we find the solution in this particular system does have one solution, if we were to find that one solution, it'd be an ordered pair that if I put in x and y into each equation, I'd get a true statement in both equations. Because the solution satisfies each equation, what that means is that the solution must lie on the graph of each equation. If it's on each equation, then it's going to be where the two lines intersect. When the solution has integer values, in other words, if the coordinates, x and y coordinates, are integers, then it is possible to use graphing. It's not the most efficient way to solve a system of equations. We'll be doing things algebraically, using substitution and elimination, but we need to maybe understand what it means to solve it by graphing. And there are basically four things that you need to go through to solve a system by graphing. The first thing you're going to want to do is write the equation in a form that's easy to graph. Generally, that would be, for most of you, writing it in slope-intercept form, y equals mx plus b. Some of you might be able to leave it in standard form and do opposite of a over b for slope and c over b for y-intercept. You also might use standard form and use the x-intercept and the y-intercept if you can find those quickly and easily. Once you've written them in a form that's easy to graph, then what you want to do is graph both equations in the same coordinate plane. That's going to result in two lines in the same plane. You then want to estimate the coordinates of the point of intersection. So find where the two lines intersect, put the dot right there, and estimate what those coordinates are. When you're graphing, you always want to make sure you do this last step, which is check the coordinates algebraically by substituting into the original equation. The key here is the original. Let's change that to yellow. Now you want to use the original. Don't use, if you had to rewrite it in slope-intercept, don't use that because maybe you made a mistake writing it in slope-intercept. Always go back to the original equation to check. Now we're going to solve a system actually by graphing. So we have two equations, 3x plus y equals 11 and x minus 2y equals 6. Again, both of them are in standard form. So what I'm going to do is take the first equation, and because it's got a y with a coefficient of 1, that's easy for me to put in slope-intercept form. I just have to put the 3x on the right side. So I'm going to put that in slope-intercept form, and right here it is in slope-intercept. Y is equal to negative 3x plus 11. And when you have it in slope-intercept, then you should be able to see that the y-intercept is 11, the slope is negative 3. That should be pretty easy to graph. Now the second equation, x minus 2y equals 6, for me to put it in slope-intercept form, I would ultimately have to divide everything by negative 2. So what I did was I went ahead and I'm going to use the intercepts. Okay, so I'm going to use the intercepts for this equation, and those two intercepts are 6, 0, and 0, negative 3. And so this is the x-intercept right here, and this is the y-intercept. And for me to find those, all I did was put 0 in for x and solve for y. That gave me the y-intercept. I put 0 in for y and solved for x. That gave me the x-intercept. Now what I want to do is just graph both of these lines on the same coordinate plane. So on the next page, I've got the lines graphed. There they are. The blue one is the original equation, 3x plus y equals 11, and the green one is the original equation, x minus 2y equals 6. Remember the graph, we had the y-intercept of 11, that's right here. If the slope is -3, you're down 3 and right 1. And so there's a few points that were used when I graphed it. On the green line, remember I used the intercepts. The x-intercept was 6, that's right here. And the y-intercept was -3, that's right there. And so then all I did was take my straight edge and draw the line. Now, the solution is where these two lines intersect. Right there's the point of intersection. This ordered pair is 4, -1, and that's the solution. Which I want to maybe check and make sure that it works. So if I put it into the first one, put 4 in. Question is, does that end up being 11? That's 12 plus -1, that's, oops, 11 equals 11, that checks. In the green equation, now you have 4 minus 2 and then -1, because that equals 6. And then that's 4 plus 2, that's 6 equals 6. That checks. And so now I've solved this system by graphing. And all you really do is graph lines, which you should be able to do. When you are graphing, you're either going to get this situation where your two lines intersect, and they can intersect at any angle. They could be perpendicular, they could be not perpendicular, but as long as they intersect, that means there's one point where it's on both lines. That one point is the solution. That's this dot that I made with the red right here. Okay, but I also have the possibility that my two lines are parallel. Okay, so it is possible that you have two lines end up being parallel, and if they're parallel, they don't have any points in common, therefore there's no solution. And then there's a third possibility where your lines actually end up being the same line, where we say the lines coincide, and when that's the case, every solution to one equation is also a solution to the other, and you actually have an infinite number of solutions. So when you solve systems, those are your three possibilities. You either get one solution like this example here, or you get no solutions because the lines are parallel, or you get an infinite number of solutions because the lines coincide.